So suppose we are asked to estimate the volume of a solid that lies below the surface z equals x plus 2y squared and above the rectangle r equals 0 to 2 cross 0 to 4. So to first understand how we're going to go about doing this, I've drawn a picture of not the actual function x plus 2y squared, z equals x plus 2y squared, but suppose we had a surface, right, and we wanted to find the area underneath this region, right? So kind of the volume, not area, sorry, the volume underneath the surface extending down within this rectangle, right? The way you would go about doing that, at least to get like an estimate, is you can kind of say, just like how with regular integrals, we kind of split up the area underneath a curve to have, I'll just draw it out really quickly. If we split up the area into these rectangles, right? And then we could use a sum to kind of predict or get an estimate for what the actual area is. We're gonna do something very similar, kind of simple. We're gonna do something very similar, but this time with these kind of rectangular prisms that extend upwards, right? So suppose we were to split up this right here. So let's say there were m, like this is m kind of section split up, and n. So like n, essentially n rows and we'll say m rows and m columns, right? Right, split up like so. And I wanted to find, well, what would the area be? Well, let's suppose each of these little rectangles have an area change in A, right? Well, then what we could do is we could pick a point on this surface. We can call it like f of x. You'll see in a second what I'm going to do here. xij, yij. And we can say, well, the area of this little small kind of rectangular prism, the volume of it will just equal whatever that function value is. Because remember, the function value gives us like the height. So it's going to equal the height xij, xyij. And for right now, this ij stuff you can just consider as a small, like a point, like, just some point on our surface. Oh, did I say change in x? Sorry, this is supposed to be change in area. So really, what you're gonna do is you're gonna sum up all of these small little volumes for all the rows and for all the columns. So what you get is a double sum. If you were to go about doing this, you would have to take a double sum, and you can say, I forgot that. Let me just check my notes. I honestly just forgot the notation for sums. I think you can say, okay, well, yeah, this is it. We could say, we will say, let's say we can say like j. Let me look at this again. Okay, j is equal to 1 to n, and then j is equal to 1 for n. So what you're doing, yeah, we can leave it like that. So what this double sum is doing is you're first going to take the sum in here, where you're going to go along, or actually, let's think about this. It's like if you've done computer science, it's like a double for loop. So if you think of like, okay, first, for I equals 1, so for I equals 1, that's the first row. We're going to go through and sum up in this inner sum at j equals 1 for the column. So I represents the rows, j represents the column. So we're going to go for this square, 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 sum it up. And then we take the next row, right? We go to I equals 2, and we start the j equals 1 all the way till n again. And that just allows us to sum up all the volumes together to get a total estimate volume. So we're going to take a very similar approach to this for this estimate. And it's pretty simple, right? Really, what we're going to do is we're going to say, okay, let's say, so obviously you can imagine we had those m and n's, right? M and n represented the number of rows and columns. And if we made those bigger, if we included more rows, I don't know why I'm about to fall over. If we included more rows and columns in our sum, you can imagine our estimate's going to be better. We're going to say, let's say m is going to equal 4. So I'm just going to check my notes. or no, let's have them both the same. So we're going to say m and n are going to equal 2. So we're going to have 2 rows, which are going to kind of look like this. So we have first row, second row, and we're going to have 2 columns, just like so. So 2 columns, like so. Now what we can do is we can use we can kind of do actually a lot of ways, right? You can choose. So what I can do is I can take a Riemann sum. That's what they're called, by the way, right? That process of taking that sum is a Riemann sum. I can take my Riemann sums considering values on the lower right corner, right? Because, you know, for this estimate, you can imagine I should never erase that. You can imagine that on your surface, the point you pick within that rectangle, right, will have different heights. So, you know, the z value at this xy coordinate might be different from this z value. Does that kind of make sense? So your height of your kind of mini rectangular prism will be different depending on which kind of point you pick. I'm going to just pick the lower right for all of them, and that'll give me a different estimate than if I were to use the top left, that sort of thing. So I'm going to use the lower right corner. So I'm going to say, okay, at this point, I know z of 1, 2. Let's see, if I plug in 1 here, I get 1 plus 2 times 2 squared. 2 times 2 squared is 8, plus 1, that's going to equal 9. And I'm going to multiply that, right? When I'm summing up the volume, right? If I were to extend this up to z equals 9, right? For my surface, I need to compute the volume. So to compute the volume, I have the height, which is 9 based off the z value, and then I just need to find the area of the base, right? It's base times height for the volume of the area of the base times height for the volume of a rectangular prism. So 9 times the area is pretty simple. It's going to be 1 times 2 for each little subsection. So the area is 2. And you're going to see in a second what I'm about to do. I could compute this out, but you're going to see in a second we can make our lives a little bit easier and kind of say, okay, well, for this square, right, I took care of this square. For this, or not square, this rectangle. For this section, I would do the same thing, find the z value for this point. So this is 2 and 2, which is the same thing as 1 and 2, but now I'm adding 1 to x. So I would get 10 times 2. And then I'm going to do the same thing. I might have wrote this wrong. Oh, no, I wrote that right. Okay, never mind. And then for this right here, I'm doing 1 and 0. So 0, z, 1 and 0. That's pretty simple. That's just 1 times 2. And then for the last lower left or lower right corner, we're doing 2 and 0, which is pretty simply 2. So when I'm going to add this up, you can see I can actually just factor out, right, all of the 2's, right? So this is really the same thing as 9 plus 10 plus 1 plus 2 times 2. So if I do this, I would get 19 plus 1 is 20 plus 22. I would get 22 times 2, which is going to equal 44 units cubed, right? Whatever the units are, it would be units cubed. So that is one estimate for this kind of the volume that lies below that surface. But another thing is I can take a midpoint sum. So a midpoint sum is exactly what it sounds. You're just taking the midpoint value. So I would go, you know, for this square right here, the midpoint x is 1/2. The midpoint y is 1, right? I just do 2 minus 0 divided by 2, 1 minus 0 divided by 2. Or in this case, I would do 2 minus 1 divided by, no, I wouldn't do that. I would do 2 plus 1, actually. And it ends up working out in this case. This gives me like the difference. I think 2 minus 1 over 2 gives me the difference, which would be 0.5 when you do it. The difference from like one of these points. To get the actual point, you do 2 plus 1 divided by 2 divided by 1.5, if that makes sense. Point is, I would just take the middle. I'm overcomplicating this. I just take the middle point, and I use that xy coordinate to calculate my z value. So let's do it again. For the first one, I have 1/2 and 3. So 1/2 plus 3 squared is 9 plus 18, right? Yeah, I think that's right. Plus 18. Wait, what? 9. Wait, why did my brain just fart? 9 squared, or 3 squared is 9 times 2 is 18, plus 1/2 is 18.5. So I'm going to say equals 18.5, and then I have z, and then 3/2, 3 this time. So this would be 3/2 plus 18, which would be 19.5, which I'm just adding 1. And then if I go down here, I'm doing 1/2 and 1. So 1 squared times 2 is 2 plus 1/2, I get 2.5. And then z of 1/2, or sorry, 3/2 1 should be 3.5, right? Because I'm doing 2 times the y value, which is 1. That's 2 plus 1.5 should be 3.5. Please comment if I've done any of the math wrong. But I'm going to add this up now. So 18.5 plus 19.5 is going to be, I believe, 38. Yep, 38 seems right. And then this will be 6. So 38 plus 6 is 44. Now I would multiply that by the area, right? I would multiply it by 2 because I added up all the z values, but I'm finding volume. So in the same way where I was able to factor out the area, because that change in, or that kind of change in area was the same, I would get 44 times 2 is going to equal 88. And once again, if any of this is wrong, just let me know. But you can see both methods had a different kind of estimate, right? Which estimate is better? You could probably figure, you could probably get the actual answer and figure that out. But the point being, there okay, my brain needs to have more focused thoughts. What I was saying about you could compare the answer. My point with that is just to say there's no it's not like lower left is always better, right? You would have to get the actual answer, compare to see which one's better. But in my guess, I would probably guess the midpoint's a better estimate in this case, because I think these lower left or lower right points, they have this is when y is equal to 0, right? So your z value is lower. So yeah, that's just how to estimate them. We're going to talk about how can we actually figure out the exact area. And as you can imagine, we're going to need a double integral. So let's talk about double integrals. Let's go back to our sum definition of kind of a volume, I guess. So basically we're saying, hey, the volume under some function v, or it's not v, sorry, the volume v under some function z, and then a rectangle on the xy plane is going to be this double sum where I'm going I equals 1 to m, and then the sum of j equals 1 to n of f of x ij, yij, times the change in area. And remember, the ij stuff, that's just saying it's kind of like coordinates, right? It's that when I is equal to 2 and j is equal to 3, it's an x coordinate at that point, kind of. You don't need to worry about this too much, but what we are getting at is, hey, your estimate, so this is really an estimate, right? I don't know why I drew that. It should be an estimate. Your estimate gets really, really good if you're making more and more columns, right? And rows, right? We did only when m and 2 is equal to 0. Or sorry, oh my god. M and 2 is equal to 0. What am I saying? Our last example was when m equals n, and when those were both equal to 2. In this case, well, to make our estimate better, I should say, you would want m and n to be 5 or 7 or 20, right? Make as many rows and columns as possible. That makes each rectangle smaller, or it makes each change in a smaller, but there's more of them. So you get a more accurate answer because you can go through more points on your actual function, right? So the best, right, is when, hey, what happens if, we take the limit as both m and n approaching infinity, right? What happens if you make as many rows and columns as possible? Well, what you get is, first of all, the true volume, right? You get the actual true volume of your function. And that is what brings us to a double integral. It's going to equal the double integral over a region R of f of xy times dA. I'm sorry, I'm just looking at my notes, making sure I've covered everything. So yeah, this ends up being for a region R, which can be defined as like, you like some like R is just any region, or I guess any region. We're gonna focus on rectangular ones, but this is the double integral. Now, suppose our region for rectangles, right? Suppose our region was this rectangle with x coordinates A, B, and then, yeah. Should we do it like that? For x coordinates A, B, and then y coordinates C, D, right? So A through B, C to D. The volume ends up being the same as the integral from, let's be careful about this. So let's do this. C to D, A to B, f of x, y, d, dx, dy. Okay, let's talk about this. So first of all, we're in it, and here we're saying we're integrating by dA, which makes sense. We're taking the limit as change in A becomes really, really, really small. But what is dA? Well, that small change in area, excuse me, I don't know why I'm burping so much. That small change in area just ends up being, if you take the side length dx times dy, right? You get dA when you multiply them. So this should actually kind of make sense. As for the bounds, what we're doing when we're taking this integral is we're saying, okay, we are going to take this small little area, or not area, we're going to sum up, let's say at this y value, so at y equals whatever, so at a certain y value, we're going to take the integral, we're going to, this is actually hard to explain. It makes sense in my head, as the thing is with teachers. It makes sense in their heads. How do you explain it? So the way I think about it is like, for all y values, what you're doing is you're taking all the z values, right? You're taking, let's draw this in, do I want to draw this in 3D? Let's draw this in 3D. If I had some surface, or whoops, okay, this is a terrible rectangle. But the idea is that it's like you're taking the volume of this sliver, not even a volume, it's more like an area, right? You're taking like the cross-sectional area. If I were to kind of draw this out, you're taking the cross-sectional area through a certain y value, right? You're going to get some area because what you're doing is you're taking dx and multiplying it by the z value, the height of the function that's coming out of the page. Because this is like an xy plane view. And you're taking that area, and then that accumulated area, I guess you're multiplying it with the dy to give you the volume, right? So you're kind of going two ways. You're getting the area and then the volume. And this is called Fubini's theorem. If f is continuous on this rectangle, then this is also the same thing as just switching the bounds, right? CD, AB, f of x, y, dy, dx. Reason being that, first of all, notice how the CDs, right, are associated with y values. So I'm going to do the integral from c to d with my bounds being c to d of f of x, y, dy first. I evaluate the inner, right? I evaluate this inner integral, and then I take the integral with respect to x. So this there's a proof for this, but the reason I like to think about it is just like when you're calculating the volume, whether you're going from whether you're starting from all the x's and then going up to get the volume, or starting with all the y's and then going through all the x's, you're still calculating the same volume. So that's why, it hopefully should make kind of intuitive sense. And if you want to find the average, right, the average value over a rectangle, you just divide this whole integral by the area of that rectangle. So let's do a couple of examples. I'm going to stop using this marker because that's not too bad, but, you know, I'll just use a different rectangle. Rectangle, like my brain is just not working well. So let me find a good example to show you guys. Yeah, I think this is a good example. So let's say we want to take the double integral r for x over 1 plus xy dA over the region, let's say from 0 to 1 to 0 to 1. So 0, 1 cross 0, 1. So first thing you gotta do is figure out your bounds, right? So I'm going from my x values, I'm going from 0 to 1, and my y values are going from 0 to 1. So I'm going to be taking, right, my double integral will have bounds 0 to 1, 0 to 1. Now, I'm going to have my function x plus 1 plus xy. And the question becomes, right, do I integrate with respect to x first or with respect to y first? You're going to see in a second. So the way this works is this integral right here, the one that I'm going to kind of box up, this is the integral we're going to want to solve first. And then that answer, whatever we get from this integral, we put it back in here, right? So, and I'll show that in a second. It'll make more sense when we actually do it. But you can see if we wanted to integrate with respect to x first, you will see that, hey, this is going to be kind of a nasty integral to solve because I have x over 1 plus x. I'm going to have to maybe use integration by parts. I can't do u sub, right? I treat the y as a constant, just like how you do it for derivatives, because in this case, we're kind of going by y, like the y is kind of treated as a constant. So we can't really do integration by parts. We can't really, like there's not really an integration technique that'll make it easy. So in my head, we're gonna do dy first. And note that this is like the same bounds for both, right? But if my y bounds were 0 to 2, right? I'm gonna change that back. I would have to make sure this is all, the inner integral is 0 to 2, because I'm doing the first integral first. I have to match the bounds, but we're just gonna leave it as 1. So with respect to y, this is actually not a bad integral to solve. If I were to do this with respect to y, dy, firstly, the x is regarded as a constant, right? Because we're integrating with respect to y. So the x value we regard as a constant. 1 over 1 plus xy dy. This is a natural log integral, and this ends up being the same as 1 over x times ln absolute value 1 plus xy. Reason being because we have the 1 over x because we have the 1 over x there because it's chain rule, right? When you have the inner, if you take the derivative of the inner, you just get x. So if you were to take the derivative of ln 1 plus xy, you would get x times 1 over 1 plus xy. But the antiderivative is 1 over 1 plus xy. There's no x. So I need to multiply by 1 over x to get rid of that. It's like reverse chain rule. So these actually cancel out, which is pretty nice. And I get ln 1 plus, and I'm plugging in 1s and 0s for y. So I get x1 minus ln 1 plus x times 0. My final answer is 1 plus x, right? Because here I get ln 1 plus 0, so ln 1 is just 0. So I get ln absolute value 1 plus x, or not, absolute value. Which is kind of weird, but because we're integrating from 0 to 1, this will never be negative within our integral, so we don't need the absolute value. All right, so now, as I was saying, we're going to replace the answer we got here. Notice how it's in terms of x. We're going to replace that with 0, 1, and then we're going to replace it with ln 1 plus x. Because that was our answer. That was kind of like our answer to this integral from within. So we replace it with the we replace it with the answer. So now here we're gonna take the integral of natural log 1 plus x, and now note that first of all, the one plus won't really make a difference here, because if you think about the derivative when you're doing chain rule, if you were to take the derivative of the inside of 1 plus x, you just get like 1. So you're just multiplying by 1. Chain rule won't really affect that. So what we can do is we can just use, you can use integration by parts to figure it out, but hopefully from Calc 2 you remember this is actually ends up being the integral x ln x minus x plus c. So really our x just ends up being 1 plus x. So we have 1 plus x times ln 1 plus x from 0 to 1. Or actually, yeah, we'll do it like this. Minus 1 plus x from 0 to 1. So now, as we're doing this, we're just going to substitute in the 1s and 0s. So I get 2 when I plug in 1 here. So 2 times ln 2 minus 1 plus 1 is 2. And then we're going to do minus, well, when I put a 0 here, I get ln of 1, which is just 0. So that term will cancel out, and then I get plus, then I will get minus negative 1 when I plug in a 0 there. So in the end, I get 2 ln 2 plus, or minus 1. I'm doing 2 plus 1, or negative 2 plus 1, which is minus 1. And then I can leave it like this. I can also simplify this to ln 4 over e. You can have fun, try to figure out how you can do that. But yeah, this has been double integrals over rectangular regions. So in the next video, we'll talk about how you can take double integrals over kind of other regions, like maybe parabolas and such. So yeah, thank you for watching.